So genetic circuits are this really cool thing where you can like tweak cells to respond to certain things in their surrounding environment. Like you can make a cell glow when it detects a toxin or something like that. And they're really cool in concept, but like they're slow. They're really slow. It's like dial-up modem level at the moment. You wait an hour for something to happen. And the reason that it's so slow is actually related to what you might have learnt in high school. You know, first the DNA has to become RNA before it can then become the glowing protein. And that's the slow part. It's like hours long. And so if you turn the circuit on and then off and then on, each time you have to degrade all of the proteins all over again. And the cells, like, you know, each time that they have to make it from scratch, they get tired. So what if we could skip all that? You know, skip the DNA, skip the RNA, just have the proteins and just have them on and off. Is that possible? Well, let's talk about it. So the answer to doing everything on the protein level is prion-like proteins. You heard of prions before? Yes? No? Well, let me tell you, they're mad cow disease. Yeah, that one. It's also Kuru, which is this awful disease associated with like cannibalism. And I'm sure that there's some movie out there about mad cow disease or Kuru starting a zombie outbreak or something, but don't panic, because actually after, you know, science kind of collectively settled down about prions being this weird whole new disease vector, we started to realize that, oh, okay, prion-likes are actually kind of benign, pretty much most of the time. The definition is generally a little bit fuzzy, but the best way that I can describe prion-likes as someone who literally did research on them, like in the lab, is that they're proteins which can selectively clump and unclump in certain conditions. So take the one that I worked on, ELF3, a plant protein, for instance. When ELF3 gets hot, its molecules stick together in under a minute. You know, think of it kind of like a molecular Velcro. It's, you know, you add heat and it instantly clumps, like putting on your shoe, which is already kind of cool by itself, but like on its own, that doesn't really do much, you know, not for our biological circuit stuff at least. But what if we then combine it with another thing? So in plant science, there's something that we use to detect things quite often, and it's called bifluorescence complementation. Basically, we take a protein that can, you know, fluoresce, and then we split it into two halves, and we fuse those halves to some other stuff. You know, let's call the other stuff in this circumstance protein A and protein B. Protein A and protein B come close to one another, then the two halves of the fluorescence protein also recombine, and then once the two halves are together, then bam! Glow city! Well, I mean, fluorescent city. Glowing and fluorescence are separate things. Fluorescence is when the light comes in and then it makes light out, whereas glowing is it makes its own light and it requires a lot of stuff. Anyway, so if you glue the two halves to ELF3's clumping proteins, at room temperature, they're apart and they're dark. But then if you heat it up, they clump, the two halves collide, and bam, instant shininess. No genes needing to be transcribed, no ribosomes, no waiting, just biology at the speed of clumping? I was gonna say the speed of light, but it's not really. Anyway, so why would this be a big deal? The first off is the speed. So genetic circuits take hours to turn on and off, whereas this takes 60 seconds. The second is the efficiency. You don't drain the cells, basically the cell's batteries, by making RNA and proteins over and over and over again and having to like break them down each time. You just have the proteins, they're on, they're off, they're on, they're off, they don't have to be transcribed and then destroyed. And the third one is related to that, control. If you want to reverse the whole thing, then you just cool things down and then the clumps dissolve and then it stops shining. It's basically just a protein light switch. But what if we swap from heat then to something else? For instance, what if we want to detect glucose levels? Imagine a diabetic with a little patch on their arm, and just before like a glycemic crash, it shines. Or, you know, maybe not just before, maybe like an hour before, so they can do something about it. Or how about something that detects, you know, fever in babies? And it doesn't have to be permanent, just like a little sticker with some literally just 100% organic protein. Or what if you go more ambitious? What if you have like factories where the yeast brewing cycle just starts on command? Or like cancer therapies that activate only to some very specific environment found in a tumor. Now, there are downsides, and it's definitely not easy to engineer this. In fact, you know, I spent a whole research project at Imperial College London investigating like a preliminary version of this, and yeah, it's not easy. For one thing, prion-like clumping is awesome in that it's super sensitive and can easily clump in response to tons of different things. You know, heat, light, acidity, even electricity, hormone levels, how close it is to other proteins, tons of stuff. But prion-like clumping, it also sucks because it's super sensitive. And even if you wanted to just respond to one of those things, it kind of responds to all of them anyway. And, you know, part of getting it right is engineering away all of those other things, which is, yeah, annoying. It's very, very specific. There are a couple of really awesome labs already doing work on exactly this domain. It's called liquid-liquid phase separation. And I'd highly recommend going to your favorite local DeepSeek or search tool or whatever you use and asking it to find the latest cool stuff on Google Scholar about it. Like, I'm pretty sure that in a few years or so, the David Baker lab, for instance, is probably going to put out some kind of AI as well that can just straight up generate new prion-like proteins. And they'll probably have perfect sensitivity to whatever we want. So it may be time for me to get back into the lab at some point, is all I'm saying. Anyway, yeah, that's kind of all I wanted to talk about today, so see you.